Hi everyone, so this video is an introduction to L2 parameter regularization, and this is basically a type of the norm penalty that we talked about before. So remember the norm penalty, basically you add to the cost an alpha, which is a regularization coefficient, times a regularizer that depends on a norm, and that regularizer is a function of theta. So here that regularizer is omega, a function of theta. Theta is all the parameters. Now, as we said before, it's typically the case that biases are not included in the regularization function because there are very few of them, and it's typically it typically leads to underfitting to include bias in the regularization function. So the regularization function is a norm that's a function of the weights, the weight parameters. So let's say the weight parameters are omega. Then L2 regularization is basically the norm, the L2 norm square. So this is the sum of the squares of every element. And then we add half to this. And this is just a technical thing here, as it will simplify our interpretation of L2 regularization. But you could remove this half and replace it by any other constant, and you will get the same interpretation scaled to that constant. Now, what L2 is doing is basically it penalizes the square magnitude of the weights, right? So if you imagine in two-dimensional, in R2, right, the L2 ball of norm 1 is a circle around the origin of norm 1, right? And the limits are here 1, 0, minus 1, 0, 0, minus 1, and 0, 1. Right? And every point here, the square, so for example, 1 over root 2 and 1 over root 2 is a point on the edge of the circle because half plus half equals 1. Right? So basically, this is trying to minimize the radius of that ball around the origin. And within that ball, these are the weights that you should have, right? So you penalize. So basically, this is a norm penalty. It's not explicit constraint. So you're adding a penalty to the cost function corresponding to the radius of that ball. If you have if your weights lie on a big ball, then you have a high regularization cost. If it's a small one, then you have a small regularization cost. Now, this is also known as ridge regression or Tikhonov regularization in recognition of how it was first introduced. So so this is just an introduction in this video. So let's just discuss the parameter update, right? And then next time we will discuss the optimal solution. So when you have a regularization strategy, you are naturally curious about how it affects the parameter updates and how it affects the optimal solution. Now, analyzing how L2 affects the parameter update is fortunately a very simple task to do. Because so the new cost function is basically the old cost function, which is J, right? Plus, so here we assume there is no bias at all, right? Just for simplicity of analysis, but you could have bias in the original network as well as in the cost function, right? But even if you have bias in the cost function and in the network, typically L2 regularization or the regularization cost is a function of the weights only. And then we add to it alpha, the regularization coefficient, times omega, which is here half the L2 norm square. The L2 norm square is given by W transpose W. Right, so if I have a vector of weights W, then if I multiply it transpose by itself, then I'm squaring every element and adding. Now, if I take that derivative, the gradient with respect to omega or W, however you like to call it, then it's the same as the gradient with respect to omega of the original cost function plus 2 omega times alpha over 2, which is alpha omega, right? Because the derivative of a scalar, so it extends, the same expression extends to vectors. The derivative of scalar, right, W square is 2W, right? So you get the 2 factor cancels the half, and that's why we had the half for convenience. So you end up with alpha omega extra term to the gradient of the cost function. Now the parameter update, the new omega is the old omega minus epsilon, which is a learning rate. And in the next section, we'll discuss in more detail what a learning rate means, right? But it basically defines, or the next section will discuss in more detail how it affects the learning optimization strategy. But every iteration of training, you take a step towards minimizing the cost function through the gradient direction. And that the step size is called the learning rate, right? So you have the omega, and then you go in the negative gradient direction because you're trying to minimize, minus epsilon, the learning rate, times the gradient, which is given by alpha omega plus the original gradient. Then you end up by 1 minus epsilon alpha times omega minus epsilon gradient omega, right? So this here, epsilon gradient omega, this is the normal update, right? Normally, I would have taken omega and subtracted from it the learning rate multiplied by the gradient of the cost function. The new thing here is that I shrink the weight before I carry out the normal parameter update. So in effect, this is what L2 regularization is doing, right? It shrinks the weight by a factor of epsilon alpha, where epsilon is the learning rate and alpha is the regularization coefficient, before carrying out the normal parameter update. The larger the value of epsilon alpha, the more aggressive this shrinkage happens before I carry out the parameter update, right? But it's really alpha what controls how much the regularization is aggressive, because even though epsilon contributes to the shrinkage, epsilon also contributes to the update. So if I increase epsilon, it's right that I'm shrinking by more, but I'm also updating by more, right? So the epsilon effect is to shrink by a factor that corresponds by how much you update, right? But the alpha effect is not in the update, in the normal update. The alpha effect is unique to the regularization added effect, right? The more alpha, the larger the value of alpha is, the more aggressive the regularization is. In the next two videos, we'll discuss the effect on the optimal solution, right? So this is an intermediary effect, how it affects the parameter update. That's what we discussed this time. Next two videos, we'll discuss how it affects the optimal solution.